Alright guys, welcome to my online lecture for significant figures, or sig figs as we call them for short. So there's going to be several online lectures for the first set of chapters for general chemistry. This one's going to deal with significant figures only, what comprises a significant figure, how we go about determining them, how to use them in calculations, and then we'll also have a couple of other sessions for scientific notation, dimensional analysis, which is converting back and forth between different units, and things like that. So let's get started and talk about significant figures. So first of all, we need to sort of ask ourselves, what are significant figures? Because they're very important to us as a group of scientists. We use them all the time in our calculations when we're communicating with one another. And the best way that we can really describe a significant figure is that a significant figure is a non-place-holding digit before or after a decimal point. So what do I mean by place-holding? Well, we'll see some examples when we go over the significant figure rules. But place-holding would be if I turn around and I say 0.0001, that 1 is going to be significant. All of these zeros are not significant. They are holding the decimal place away from the 1. And if we go, we've got the tenths place, the hundredths place, the thousandths place, and the 10,000ths place. So this could really be written in scientific notation as 1.0 times 10, and it would be to the negative 4. Okay? Because if I did move this over, I would get 1, 2, 3, 4. And then I would have the 1 there. Okay? You could also write it as 1 times 10 to the negative 4th. This would be 1 sig fig. This would be 2 sig figs. The 0 after the 1 there would be a significant figure. Okay? Now, if I have a value like this, 1.000, so it's 1, but with 3 zeros after the decimal point, these are all significant figures. These zeros are not placeholders because they're not coming before the first non-zero digit. And again, we're going to talk about this when we go over significant figure rules. All right? So, when we talk about significant figures, there's something that's pretty important in terms of what they actually, their significance, or we call them significant figures, okay? So, if a figure is significant, what's significant about it? What is it telling us? All right? So, let me just work on erasing some of this here. So, when we deal with a significant figure, what's actually significant is basically the figure is telling us how much certainty there is in our measurement. And that's important when we're scientists. So let's say that a balance turns around. We weigh something out, right? And we get I hope I'm still on eraser here. Sorry, guys. And we get 1.526, right? So that's the value that we get. And we're weighing this out on a scale, or a balance of some sort. The uncertainty in this and any number lies within the last digit on the right. So that's our level of uncertainty. So we're certain of these 3 digits right here, 1.52. We're certain of that. And then whenever you have your instrument, it's normally going to have some sort of a what we call like a error range, okay? Sometimes it's called a standard deviation, how far out the error can go, all right? But we have basically 0.00, let's say 1, all right? So plus or minus 0.001. That's what the balance says. So if I pull out the the instruction manual or the owner's manual for the balance, it's going to say, oh, our balances are calibrated up to 0.001, or the thousandths place, and there could be variation within that last digit right there, which is the 6. So what that really tells me is I'm certain of my 1.52, but it really could range from plus 1. So if we did the plus 0.001, that 6 would become a 7, and it could be all the way down to 1.525, because if I took the minus portion right there, and I subtracted that from the 6, then I would have 5. So it's basically saying somewhere in this range, the balance is sure that that's what you have. All right, so there is a level of uncertainty because that is a range. I can go from 1.525 to 1.527. So the 6 is my level of uncertainty. The more significant figures I have, so let's say that I turn around, I'm going to erase again for a second here while I'm talking. Let's say I turn around and I use a balance that has a better set of significant figures. So usually the significant figures that we obtain are going to be limited by the instrument we're using. So for instance, a ruler, it's going to stop with millimeters. That's about as close as we can get with your standard ruler that you would be using. If we go past millimeters, we're talking about some very highly calibrated distance measuring tool. All right, that's going to give a lot more precision and a lot more certainty in our measurement. So let's say they have things like analytical balances. Let's say that I get a balance and I say it's 1.52, and this time when I read my digital display on the balance, it says 654. All right, so now my level of uncertainty is right here. It's with the 4. And so maybe I consult the manual and it says 0.00002 plus or minus. And that's the range of the calibration for that. All right. So then I'm talking about this last digit could be up to a 6 or down to a 2. But this is still much higher in its certainty in my knowledge of what I have versus before. Because before I went up to the 6 and then I had to stop. Now it's telling me, oh, you have the 6, you have the 5, and it's really the 4 that we're uncertain about. So as I continue to go up in my significant figures, I'm going up in the certainty of my measurement, and I can, the more certain my measurement is, I can provide reliable results that are repeatable for other scientists, right? So that can be a big difference if I have very specific measurements and I turn around and I go, oh, I have something, and this value or this unit is 2. Well, that might be very different than if I say, oh, it's 2.1, which might be different from me saying, oh, it's 2.167, etc. And I could continue going out and out. The more information and detail that I can provide in my data, the better off it's going to be in terms of its certainty. The more validation I'm giving to my study and to my data. All right, so that's the point of significant figures. It's a way of communicating to the scientific community how certain you are in your measurements. And the more certain we are, that's a good thing. The better it is. All right, so let's move to the next point here. There are several rules we're going to use when we deal with significant figures. All right. So, for significant figures, there's really 5 rules. I listed 4 here. The 5th one, we define what an exact number is, but it's really sort of a rule that you should know. So let's talk about these. Number 1, all non-zero digits are significant figures. All right? And I'm going to go ahead and I'm going to mention that is digits 1 through 9. So some people a lot of times will say, oh, well, how come, so that goes with this. So a lot of people sometimes will say, how come, 12 isn't included in that? Well, the reason 12 isn't included in that is that if I look at 12, 12 has 2 significant figures. The tens place has a 1, and the ones place has a 2. So those are 2 significant figures. After we go past 9, we get to 10. And at that point, you have 2 figures instead of 1. So we're cycling through again and again. So it's not that 12 isn't a significant figure. It's that it's comprised of 2 non-zero digits. Each one is a significant figure, so 12 is 2 significant figures, whereas 1 or 2 by itself would only be 1 significant figure. So rule number 2, all zeros between 2 non-zero digits are significant. So what this is saying is, let's say that I turn around and I have something like 1,001. Sorry, that 0 got a little cut there. If I have 1,001, these zeros between the ones are significant because I have a non-zero here and a non-zero here. So maybe I have 5,063. If I take 5,063, the 0 in between the 5 and the 6 is significant. All right? So what this is basically saying is anytime I have zeros, no matter how many I have, if they are wedged between 2 non-zero digits, they are going to be considered significant digits. Okay, so hopefully that makes sense. All right, so rule number 3. Any zeros before the first non-zero digit are placeholders and are not significant. So you'll notice Rule 1 talks about non-zero digits being significant. So Rule 1 deals with 1 through 9. All the other rules are dealing with zeros, because zeros are really where we start having uncertainty in whether they are significant or not. So when we're talking about Rule 3 here, it says any zeros before the first non-zero digit are placeholders and they're not significant. So where we usually see this is when you get 0.00000, etc., and then 15 or something like that. Here, the 1 is our first non-zero digit. So again, this is if they come before. All right. So any zeros before the first non-zero digit are placeholders and they're not significant. And if you go back to the beginning of this lecture, we were talking about, all right, a significant figure can best be described as any non-place-holding digit. Well, all of these zeros are holding places. What they're really doing is saying 1, 2, 3, 4, 5. So I could rewrite this as 1.5 times 10 to the 5th. I got cut off there a little bit. It would be times 10 to the 5th. All right. So again, anytime you've got zeros coming before your first non-zero digit, they're going to be non-significant, those zeros. So how about zeros that are coming after a non-zero digit? So we certainly have situations where we get, the number 1,000. All those zeros after the 1 are after the 1, which is a non-zero digit. So if you look at Rule 4, zeros coming after a non-zero digit are always significant unless there is no decimal. All right? So that's what's really going to differentiate it here. If there is no decimal, then we usually change it to scientific notation to give significant figures. So we're not sure. So I'll give an example of that on the next page here. But I want to finish up and talk about exact numbers. So an exact number is a discrete whole number with no uncertainty. So what does that mean when we say that? If you say that something can be measured as a discrete whole number, you're talking about that it can't be split down or it can't be extended into more specific digits. So usually this is when we're dealing with specific items. All right. So for instance, I have there 1 marker, 3 apples, 5 $1 bills. Those are all discrete objects. I can count 3 apples, and I have 3 exact apples. I may turn around and say I have 3 grams when I measure it out on the scale, but that's only up to the scale certainty in that digit. There's going to be more significant figures somewhere down the line. The one exception when we start talking about this is for exact conversions. So for instance, if I say there's 12 inches in a foot, there are exactly 12 inches in 1 foot. So 12 inches in that case, when I'm talking about it as a conversion factor into a foot, is an exact number. Okay? If I'm talking about, I measured the length of the paper and it's 12 inches, well, that's based on my best measurement with my tool. So that's going to have significant figures. And we mention exact numbers here because exact numbers are in a special camp. They have an infinite number of significant figures. So you see there it says 1 marker can be labeled as 1.000 all the way into infinity. That's because 1 marker is exactly 1 marker. It means that there's an infinite number of zeros after that because I know exactly how many markers I have. There's no uncertainty in it, and I can't have 1.5 markers. I can't have 1.386 markers. I have 1 marker, or I have 2 markers, or I have 3 markers. And the zeros can continue indefinitely past that. All right. So let's go back here to number 4 with the decimal point, and let's get a nice blank page here to work with. So when we're talking about this, we're talking about basically, let's pick out the number 5,000. So if I have 5,000 and I put a decimal point there, and sometimes you'll see teachers that'll put a decimal point here and leave it like that, and that's legitimate. A lot of times, and I prefer to do this, you put a 0 after it or some other digit. Okay? And then let's look at it with 5,000 like this. So what Rule 4 is saying, if we glance back at it for 1 second, zeros coming after a non-zero digit are always significant unless, so here's the caveat, there is no decimal. So there's a level of uncertainty when there's not a decimal. So here, there's a decimal. So we're saying 1, 2, 3, 4, 5. This would have 5 sig figs. without question. All right. If we look down here, the 5,000 doesn't have a decimal. So some people get a bit confused on how you would really report this. So we'll talk about converting it to scientific notation in a minute. But the way that this would really be reported is that we would say, I have at least, how many do you guys think? I would have at least one sig fig. And the reason for that is that 5 is a sig fig. It's a non-zero digit. So if we go back and we look at Rule 1, all non-zero digits are significant figures. So regardless of whether there's a decimal there or not, the 5 is a significant figure. The question is these zeros. Are those zeros significant figures or not? Well, with the decimal, we can't tell. So the way we report it is there's at least one significant figure. Now, if we wanted to convert this to scientific notation, we know that 5,000 is a 10 to the third unit placeholder. So in other words, if I did give a decimal to 5,000 like I have up here, if I move it back 1, 2, 3, that's 3 times, so 10 to the third. And 10 to the third equates to 1,000. So it would really be, you could rewrite this as 5 times 10 to the third. 10 to the third is an exact number. We're saying it's exactly 1,000. We're converting these units into a base 10 unit. And then we're saying 5 is just one sig fig. So now we officially have one sig fig without any doubt. So here you would say it's at least one sig fig. You can convert it into this and say now it is one sig fig. Definitively no more. If you wanted to make it 2, you could say 5.0 times 10 to the third. And now that decimal there, the 0 is coming after a decimal. And again, if we go back here, okay, number 4 says zeros coming after a non-zero digit are always significant unless there is no decimal. So if there is a decimal, they're always significant. Okay? So this concludes the portion of what determines a significant figure, things of that nature. So now we want to sort of move into with mathematical calculations. So hopefully you guys remember when you're doing a mathematical calculation, you need to follow the order of operations. So some people have the mnemonic PEDMAS, or please excuse my dear Aunt Sally. Basically, the P is parentheses, the E is exponents, okay? The D is division, the M is multiplication. These guys sort of get grouped together. And the A is addition, and the S is subtraction. These guys get grouped together. So what we say is, first, you need to do anything in parentheses. Next, you need to do anything that's exponents. Next, you need to deal with your multiplication and division. Those come before the last one, which is addition and subtraction. All right, so it is important. You should go back and review this if you don't know or remember the PEDMAS. But when you're dealing with this, it's important that you always follow your order of operations. All right. So let's talk about significant figures in calculations. When we're doing calculations and we're dealing with significant figures in calculations, it's easy to, go and look at a number and say, this is how many sig figs I have in this number. But what if we have multiple numbers and we're adding, subtracting, multiplying, dividing, etc., doing that sort of stuff with them? Our answer may have more significant figures because let's say we have a couple of different things we multiply together and then we get a run-on number or a repeating number. That can go out into infinity, right? Just like pi has an infinite number of digits extending outwards, some of our mathematical answers can extend out to infinity, or they can certainly be extended well beyond the original number of significant figures we had. And we need to determine at what point we're going to cut that off and show that our answer has certainty. So in other words, our answer has to have some level of certainty just like our measurements did. We don't get to gain unwarranted certainty in our answer just because the digits were extended through the mathematical calculations. So there's two major things that we deal with when we're talking about this. So the first and the easier one to usually conceptualize or understand is the multiplication and division, right? So this is when we do the multiplication and the division. So when we do multiplication and division, the rule is basically you're going to take and look at all the measurements that are being included in this, and you're going to, when you calculate it, your answer is going to have the least number of significant figures that was present. All right. So, for instance, if I take 0.56 times 3.1245 times 8225. We'll say 67. All right. So let's say I take this. I'm going to multiply 0.56 times 3.1245 times 8,225.67. What this rules, or the significant figure rules, say for multiplication and division is your answer can only have the number of significant figures that your lowest or your least amount of significant figures in your measurement does. So if you look, this one has 2, this one has 1, 2, 3, 4, 5, this one has 1, 2, 3, 4, 5, 6. So that means the answer to this could only have 2 significant figures. All right. If you end up getting a large number, you're going to have to convert the number into scientific notation, and your scientific notation will say x dot x, where x are 2 different digits, times 10 to the y, whatever y's power is. All right. So for multiplication and division, again, you are going with the smallest number of significant figures in each of your measurements. That is what your answer is permitted to have. When you deal with addition and subtraction, and this one is still relatively easy, so when we add or subtract, all right, the easiest way to do this when you're starting out is to line them up. So let's say I've got 5.632 and 1.4 and 3.71. All right. So let's say I'm going to add these, and again, addition and subtraction follow the same rules. So where we draw the line for significant figures when we're adding or subtracting is we find the value or the measurement that cuts off at the earliest decimal spot, and that's this guy here. All right. So in other words, I go 1.4, and then there's no other decimal places after that. So this one goes out 3 decimal places, this one goes out 1 decimal place, and this one goes out 2 decimal places. So the place where they all align, right here, that's where I'm going to drop or stop my significant figures in my answer. So if I add this, all right, I would have 2. Here I would have 4. All right, so if I'm going to add this, my 6 and my 4 are 10, and my 7 would make 17. Point, carry the 1. So I've got 5, 6, 7, and then 10. All right here. So if I look at this, where I have to cut off my answer, it's right here. So 4 is going to allow me to round down. That's going to get chopped off. So the proper answer here is 10.7. All right. Now, if you have, let's say we have a problem like this. So let's say I take 0.32 plus 5.1 times 0.2. All right, so let's say I have something like this. In parentheses, I have to solve this first. Addition has different rules than multiplication does. So when I'm dealing with this, I need to go ahead and I need to work on this as an addition problem, find the answer with the proper significant figures, plug it back in, and then I can execute with the multiplication rules. So if I'm going to do this, I'm going to turn around and I'm first going to take 0.32 plus 5.1. So the addition subtraction rules say these align right here. So I get 2, 4, 5, like this. So the 2 needs to get dropped off because the 4 spot is where we align to with our lowest decimal spot. So I get 5.4. The 5.4 can now carry over into, because it has the proper sig figs, the 0.2 like this. So what I would then do is I would be able to take the 5.4 times 0.2, and that would be the next equation that I would solve. And now I'm being subjected to the multiplication rules. So when I'm subjected to the multiplication rules, the rule says that I'm going to use the least number of significant figures out of all my measurements in my answer. Well, here the 5.4 has 2 significant figures, the 0.2 has 1 significant figure. So if we solve that, all right, it would come out to equal 1.08. So if it's 1.08, I can only use 1 sig fig, the 0.08 drop off, so I would report this as 1. Alright, so I'm going to wrap that up there. That concludes how to add, subtract, multiply, and divide with significant figures, as well as what determines a significant figure itself. Thank you guys for watching. As always, check out the other videos. Subscribe if it's helping you. And please like or thumbs up the video if it's been helpful or useful. Feel free to leave comments or suggestions. And I will see you guys next time.